let's actually start with the presentation. So, good morning, everyone. We will be basically talking about the large language models towards CIoT. And one second, just trying to go to the next slide. All right. Okay. So, large language models, or which I will be using LLMs for short, are advanced artificial intelligence systems trained to predict the likelihood of word sequences. This foundational ability enables them to perform tasks like language translation, text summarization, and even creative writing. But what sets modern LLMs apart is their reliance on neural network-based architectures, particularly the transformer model, which replaced older rule-based statistical methods. Let me give you a sense of scale. Early models worked with tens of millions of parameters. Today's LLMs, like GPT-4, works with hundreds of billions of parameters. So why are they important? Because this shift in scale and architecture has fundamentally transformed industries. For example, in healthcare, LLMs help doctors analyze patient records and suggest treatments. In education, they provide personalized tutoring systems that adjust to a student's learning pace. Across sectors, LLMs have made human-machine interaction more intuitive and impactful. So to understand how LLMs achieve such capabilities, let's look at their key components. First is the tokenization process. This is the process of breaking text into smaller units like words, subwords, or even individual characters. Why is this important? Because LLMs can process data in these smaller chunks. For example, take the sentence, "The cat is sleeping on the mat." Now we will try to tokenize this. So the word level tokenization would be "the cat is," so every word is separated. And then at subword level, the tokenizer, what it does is the word sleeping may actually be split into sleep and ing. So this approach actually helps the models handle rare or unfamiliar words by breaking them into known components. Then we have the embeddings. After tokenization, these chunks, the words or subwords, whatever you tokenized into, these chunks are converted into dense vectors. So this dense vector representation is called embedding. This is where the model starts to understand meaning. There are two types: static embeddings, like word-to-vec, and there is contextual embeddings, which is basically derived from LLM's layers, varying with input context. For instance, the word bank might have different embeddings depending on whether it's used to refer to a financial institution or a river bank. These embeddings capture semantic relationships in a way that allows the model to reason about context. Then we have the attention mechanism. Introduced by the transformer architecture, attention attention mechanism allows the model to focus on the most relevant parts of the input. This is crucial for understanding complex relationships within a sentence or document. Self-attention computes relationships within the input sequence, and cross-attention is used in encoder-decoder architectures for translation tasks. They're just two different types. So here in the sentence again, if we take an example, the sentence is the cat that chased the mouse is sleeping. Here attention actually helps the model understand that is sleeping phrase is actually referring to the cat and not the mouse. So that is what attention mechanism is. Then we have the pre-training. So this is how LLMs learn general linguistic patterns. They are exposed to massive data sets, often billions of sentences, to understand grammar, syntax, and semantics. The goal is to equip the model with general linguistic knowledge. For example, models like BERT are trained to predict missing words in sentences, such as this example here, the cat, and then we mask or hide the word, and then we write on the mat. Now the model will actually try to predict what that hidden word, the word that we have masked, is. So it will predict that it is sat because it seems the most probable. And finally, we have the transfer learning. Once we have pre-trained the model, the LLMs can be fine-tuned for specific tasks like sentiment analysis. So sentiment analysis is like finding if a certain sentence has positive sentiment or negative sentiment, and or like medical diagnosis with minimal labeled data. This adaptability makes them incredibly versatile. There are again two types. Fine-tuning, which is training the entire model on the task-specific data, or it's prompt tuning, which is adjusting prompts to achieve desired outputs without changing the model weight. So one is basically you have to use the whole model to train again, or you only use specific phrases, which we call prompts here, to get whatever output you want. An example of this is basically classifying the customer reviews as positive or negative, which I said was sentiment analysis. Now, LLMs have three primary capabilities that make them so powerful. The first being text understanding and generation. At their core, LLMs can generate text that's coherent and contextually relevant. So applications range from automated content generation to translation across multiple languages and even summarization and paraphrasing. Then the second is knowledge representation. LLMs encode vast amount of information within their parameters. This enables them to answer complex, domain-specific queries. For instance, an LLM could explain the concept of, say, quantum mechanics, or even provide a summary for a medical condition. So it's basically used for real-time factual queries and educational tools or tutoring systems. And finally, we have the multimodal capabilities. The latest models integrate text with other types of data like images or audio. So for example, an LLM can generate captions for an image or summarize a video or even analyze charts and tables. This makes them indispensable for multimedia analysis. Now, modern LLMs are more advanced than ever due to their key innovations. So these are the 5 key innovations. Enhanced contextual understanding is the first one. So modern LLMs excel in grasping nuanced meanings in text by using advanced attention mechanisms like transformer architectures. They can understand subtle relationships between words, enabling tasks such as sentiment analysis, summarization, and answering context sensitive questions. So, the previous example that we saw, where the model was trying to interpret phrases with multiple meanings, like she saw the bank by the river, where the word bank should be understood contextually by the LLMs. Then LLMs also have longer contextual memory. Now, what this means is that LLMs can process and retain larger sequences of input data, allowing for better comprehension of long documents or conversations. If you have used GPT before, models like GPT-3 actually forgot a lot about the conversation after a couple of messages. But then models like GPT-4 utilize improved positional encoding and memory mechanisms. So it can be useful for legal document analysis, scientific research papers, or long-form customer service dialogues. So again, an example of this would be to analyze a 10-page research paper to provide an executive summary without losing any context at all. Then we have the few shot and zero shot learning. We will talk about this after a couple of slides, but for say general, like for starting off, in few shot learning, models learn new tasks with minimal label data by leveraging in-context examples. And in zero-shot learning, models generalize to entirely unseen tasks by understanding task descriptions or instructions. So again, quickly I'll just say few-shot learning is we give them a couple of examples and then the model tries to give the answer. In zero-shot, we do not give any kind of examples for the task and then it tries to give us the output. So the application of few-shot is training on minimal data such as some medical diagnostics, which does not have many findings yet. And applications of few-shot is basically, few-shot was training medical data, and then zero-shot was, again, translating very rare languages or generating code snippets with just a description. So say like you give a prompt, translate this English text to Spanish without giving any example to some model, and the model will try to accurately perform the task without any prior fine-tuning. Then we have the multimodal capabilities, which we talked in brief before. The LLMs are increasingly capable of integrating text, image, video, and audio data to perform holistic analysis. This enables applications such as video summarization, generating captions for images, and text-to-image generation. Applications would be vision language models for captioning, analyzing medical imagery paired with patient reports. So a model can generate captions like a dog playing in the park for a given image, which has a dog and a park in the background. And controllable and fine-tuned outputs is again one of their key innovations. So fine-tuning allows LLMs to adapt to specific domains or or stylistic requirements. Example, legal or medical text generation. And these controllable outputs enable adjusting tone, complexity, or structure to fit specific needs. Again, if you have seen in Grammarly, there is an actual option where you can choose, I'm writing this for academics or I'm writing this for a friend. So you can change the tone of your text. So the applications here are generating formal reports for business, conversational responses for chatbots, or creative content for storytelling. So it'll be like tuning responses to sound professional for a business context or empathetic for mental health support. So now let's look at the key benefits of these modern LLMs. First and foremost is the transparency and flexibility. Transparency ensures that these LLMs are explainable, providing insights into how decisions are made. Again, if you have used GPT, you will see that it tries to write what it is thinking and then gives you the output. So that is the transparency that it's going for. And flexibility allows systems to adapt to changing requirements, ensuring scalability across diverse use cases. Just like AI-driven dashboards providing, say, clear justification for why it is recommending a certain thing in healthcare or, say, finance. It can even be used, say, a professor is using an LLM-powered assistant to revise a syllabus based on student feedback, demonstrating adaptability in the curriculum design. And maybe we can even take an example of an LLM-powered loan approval system that explains why an applicant was approved or denied. So this builds trust with the users. Then we have the cost savings. So automation powered by AI reduces the manual intervention, cutting costs significantly. So it helps optimize resource allocation, ensuring efficient processes and minimizing waste. So automating administrative tasks like scheduling office hours or managing course enrollments, allowing professors to actually focus more on teaching and research. And then we have the collaboration and innovation. So LLMs foster collaboration by integrating seamlessly with existing tools and teams. So we can say this is like using LLMs as a group brainstorming tool in classroom setting to generate innovative project ideas. It can also help in identifying trends in student performance across multiple semesters to improve teaching strategies. And finally, we have the customization and adaptation. LLMs can be again fine-tuned to cater to specific needs, whether it be for individual students or, say, unique academic requirements. Adaptive learning systems evolve with data, maintaining relevance over time. This can even be seen in personalized recommendation system on Amazon, like providing tailored product suggestions based on your browsing history or previous purchases. Similarly, how Netflix will show you some suggested shows or movies based on what you've already watched. So these benefits highlight how LLMs not only improve efficiency and cost effectiveness, but also allow everyone to innovate and stay competitive. And of course, if we have talked about the positives, we need to look at the negatives of LLMs. One of the major issues, I would say, is hallucination. So these LLMs sometimes generate incorrect or made up information that sound believable, but actually are not true. This happens because the LLM might guess or lack enough real world facts while it's being trained. So this reduces our trust actually in the LLM outputs. And then especially in critical fields like healthcare or finance, where it could lead to poor decision making. I mean, take an example, say a chatbot is falsely claiming that a product has certain features which actually doesn't exist, leaving users confused. Next is the hidden costs. Initially, we may not realize that these hidden costs exist because as users we don't see it, but in organizations like companies, even universities, they can reduce operational cost, but deploying and maintaining these advanced models actually involves significant expenses like the infrastructure, computational resources, data labeling, and integration efforts. So organizations would need to invest in high performance servers, ensure regular software updates, and allocate resources for training staff to use the system effectively. And even training a large language model like GPT-3 requires millions of dollars in hardware and electricity, which we may not think of at first. Another challenge is data security and privacy. So LLMs rely on huge amounts of data, including sensitive or proprietary information, which raises the risk of security breaches or misuse. A clear example of this would be how in image generation models, they often scrape the digital artwork from internet without consent. This not only violates artists' rights but also affects their livelihood, as their unique styles can be copied without acknowledgement or compensation. There are also intellectual property issues, which again ties back to our data security and privacy part as well. So these LLMs might use copyrighted materials during training, leading to disputes about ownership. So if a generative art model produces an image resembling a copyrighted painting, it could result in legal conflicts. Questions also arise about who owns the outputs generated by these models. Does it belong to the AI developers, the users, or no one at all? Finally, there's the challenge of scalability. Scaling AI across organizations or industries is tough because of the financial and operational hurdles. You may think it's easy, but it does require some finances and operations that we don't think about. A model designed for one task may actually struggle to adapt or handle larger data loads. So a recommendation system may work for, say, a small online store, but it form when they want to scale it to a global retailer because it requires costly modifications to handle the increased complexity. So it's very crucial to address these challenges to fully realize their benefits responsibly. Now that we looked at the pros and cons of LLMs, let me actually show you how LLMs have evolved over the years. This timeline highlights the key milestones that have shaped the development of these powerful systems. We start in 2017 with a groundbreaking paper, which is Attention is All You Need. This introduces the transformer architecture, which actually revolutionized the natural language processing. The key innovations were self-attention and parallel processing, which actually allowed the models to understand relationships within text more efficiently. Then in 2018, we see the introduction of some really pivotal models. First, we have the Elmo, which introduced contextual embeddings. Then we have the GPT-1, which was released by OpenAI. And finally, Google released BERT, which significantly advanced NLP tasks like question answering and classification. Then we have the era of scaling, which is from 2019 to 2020. In 2019, scaling became the focus. GPT-2 showcased incredible text generation abilities, producing human-like text and marking a leap in AI capabilities. And then by 2020, we had GPT-3 because of its massive scaling and ability to handle tasks with minimal examples, which I said was zero shot or few shot. Then we had the specialization and innovation part from 2021 to 2022, where we got they focused on improving safety and user alignments, while tools like GitHub Copilot also came along, which revolutionized how developers write code. And then we had the modern advancements, which is 2023 to current. So in recent years, AI has become more capable and accessible. We had GPT-4 introduced, which was multimodal features, working seamlessly with both text and images. Then we had a lot more models, which brought AI to smaller devices while balancing performance with resource constraints. So this timeline actually reflects the rapid evolution of capabilities in LLMs. Early models focused on static embeddings, but today we have dynamic, context-aware systems. So looking ahead, the focus will be on making models more efficient, scalable, and aligned with human needs, ensuring they are ethical and responsible and practical for real-world use. Now, we will actually be doing a deep dive into some of the main capabilities of LLMs, which is actually important to us now. LLMs are very good at communicating and interacting with us. They have really good dialogue capabilities like maintaining context-aware multi-turn conversations, and they also adapt tone, style, and complexity to suit user needs. So these abilities can actually be seen in virtual assistants that you all use today, like Alexa, Siri, or Google Assistant. So these are like, you can even see it in chatbots for customer support and even therapy or mental health tools offering empathetic responses. LLMs are also good at handling reasoning and task execution, which are among their most impressive capabilities. LLMs excel in logical and analytic thinking. They can perform both single-step and multi-step reasoning, which allows them to solve complex problems like arithmetic and also provide common sense explanations for these answers. So, two key reasoning approaches that make this possible are chain of thought or CIoT reasoning. So this approach actually breaks down complex problems into step-by-step solution. Instead of jumping to the final answer, the model will explain each step in its reasoning process. Then we have the latent multi-hop reasoning. So this method enables the model to derive insights by connecting indirect pieces of information. So another significant capability of LLMs is, again, to execute the tasks through zero-shot and few-shot learning. Like I said before, in zero-shot learning, the model completes tasks without any prior examples. It relies entirely on natural language prompts. And in few-shot learning, the model is given a few examples to guide its response. This enhances its accuracy and performance for more specialized tasks. So the applications here would be in decision making and planning support and adapting to unique user queries without explicit retraining. So now let's discuss how these large language models integrate with the IoT systems, which is Internet of Things systems, to create smarter, more context-aware environments. One of the key advancements in IoT integration is actually the context-aware user behavior prediction. This involves using data from various IoT devices, like your smartphones, wearables, like your smartwatch, and smart home systems, like your Google Home or any of your Amazon Home things, which anticipate these user needs. For example, data from a smartwatch tracking your heart rate can provide insights into your fitness level or stress level, which can be used to recommend activities or suggest breaks. These systems combine multiple data sources like GPS, Wi Fi signals, and sensors to create a detailed picture of user behavior. Again, applications for this would be personalized recommendations like nearby services or activities, automation in smart homes and devices, and healthcare and wellness monitoring. Then, large language models also enhance the IoT systems by providing advanced reasoning capabilities. The first way LLMs support IoT is through seamless integration with sensor data, like we talked about, to generate the actionable insights. So it can actually also include things like thermostats and some smart home appliances. It can even be your fridge or microwave oven, which actually collect massive amount of data. Then the LLMs process this data, identify patterns, and recommend actions based on these patterns. Actually, we can take an example of a smart home system which might adjust the temperature or lighting based on user preference and routines. This integration enables the IoT systems to function more intelligently and autonomously. So, we talked about what zero shot and few shot learning are. So now you may be able to easily understand one of the most impactful techniques in reasoning, which is zero shot reasoning, and then we will talk about few shot reasoning. So the reasoning part here is allowing the LLMs to handle the new scenarios again without requiring additional training and making them think for themselves. So this is actually especially useful for dynamic, ever-changing IoT systems where retraining the model might not always be feasible. An example of this again would be predicting energy consumption based on user patterns and adjusting the home systems dynamically. Now let's dive into a real-world example of IoT integration, which will be the healthcare monitoring powered by cognitive IoT. So IBM Watson Health actually uses IoT devices like wearable sensors and medical equipment to monitor patient health in real time. This system is designed to collect, analyze, and act on patient data, enabling healthcare providers to deliver timely and personalized care. So, by combining IoT with AI, Watson Health ensures that critical health metrics are monitored continuously and these anomalies are addressed immediately. So, here's how the system works step by step. First are the sensors. So, wearable devices and medical sensors measure your vital signs such as heart rate, blood pressure, and glucose levels. These devices act as the first point of data collection, capturing all the essential metrics directly from the patient. Then we have the data collection. The IoT devices actually transmit this real-time data to a centralized cloud platform. This ensures that the information is continuously available for analysis and decision making, no matter where the patient is located. Next is the AI analysis. So once this data reaches the cloud, AI algorithms and machine learning models analyze it to detect anomalies. For instance, the system might flag irregular heartbeats, signaling potential cardiac issues that needs immediate attention. Finally, we have the actionable insights. If an anomaly is detected, the system generates alerts that are sent directly to doctors or caregivers. These alerts enable healthcare professionals to intervene quickly, preventing minor issues from escalating into major health emergencies. So it again enables personalized treatments, and it significantly reduces the hospital readmissions by predicting potential health issues early. A specific example of this would be a diabetic patient is wearing a device that monitors their blood sugar level. If the system detects a dangerous dip in the glucose, it immediately alerts the patient to consume something sugary, and if necessary, notifies their doctor as well. So this is very simple but very effective process. So it can prevent severe complications and save lives. The next example is the smart traffic management system. So this uses IoT sensors installed on roads and AI technologies to monitor and analyze traffic conditions. So it basically works in 3 key steps. Again, data collection, where IoT sensors and cameras collect real-time data on vehicle density, speed, and accident. Then there's cloud processing. So the collected data is then sent to a centralized hub or cloud platform where the AI models analyze it. And then we have the dynamic control, which is the collected data then is used for providing insights, right? So these insights will tell us what should be adjusted, which traffic signals need to be adjusted in real time for easing out the congestion. So this actually helps in overall traffic buildup. So the impact again is the reduced average commute time of the users, and there's also lower fuel consumptions and emissions, contributing to environmental sustainability. So a great real-world example of this is actually the traffic management system in Barcelona. In Barcelona, they used IoT-enabled smart traffic lights, adjusting dynamically during peak hours, reducing congestion and smoother traffic flow. So this city has actually managed to improve its traffic conditions significantly, and it's actually providing its blueprint to other cities to follow it. Now let's explore how advanced reasoning enhances the IoT capabilities. So again, we will go back to our zero-shot and few-shot, but this time we will be talking about the chain of thought capability. So this is actually a prompting strategy for LLMs that provides, again, adding simple instructions like let's think step by step to the input, enabling logic and multi-step reasoning. And again, unlike few-shot, zero-shot chain of thought does not require training on specific examples, making it general and efficient approach for such tasks. So the key idea here is to encourage the model to generate intermediate steps rather than jumping to the final answer. So that is the chain of thought part of it. So again, example I would show you is if we ask the model, if 20 apples are bought and 5 are used, how many are left? And then you give it the instruction that you have to think step by step. The model will give you the steps that it's thinking about. It will tell that, it's thinking first there are 20 apples and then 5 apples are used. So then it'll show you how it's subtracting and then giving you the final answer. Again, another example in case you want one, to understand it even better. We give it a problem that, there are 16 marbles and then 8 are red. What percentage of the marbles are red? And then it's again thinking step by step. So it's writing everything that is thinking, there are 16 marbles, 8 are red. So then it will calculate the percentage and then finally give you the percentage. So from this part, it will tell you like, this is what I'm, thinking about. This is how I'm getting to my answer. So it can show you how, the logical reasoning is without, again, prior examples. Then again, we come back to few-shot chain of thought. So this one again uses examples to guide the model in solving very complex tasks. So we have to actually give it explicit examples of reasoning. So this helps unlock higher accuracy in tasks which requires logical or multi-step reasoning. So it actually helps in math word problems or symbolic reasoning and common sense reasoning, where intermediate steps are critical. So the key idea here is to basically provide a few examples of problem solving as input to demonstrate how the model should approach similar tasks. Again, there's like the same kind of examples you can show. There are 5 apples, you buy 2 more, how many apples do you have? And then you're giving it one example that, let's think step by step. You start with 5, you buy this, and this is the answer. And then you give it another example, then you ask it a question. So maybe, you give these 2 examples and then you ask the same question that you did in the previous example, where, we had 5 apples and you used up 2. What happened finally? So this is what few-shot chain of thought would be. So again, let's compare the zero-shot and few-shot chain of thought to understand their strengths and limitations. So the zero-shot chain of thought here is highly flexible and fast to implement. It does not require task-specific examples, making it ideal for general-purpose tasks. However, its performance can be limited on complex tasks. On the other hand, few-shot chain of thought provides significantly better accuracy for multi-step or domain-specific tasks by guiding the model with examples. However, it requires carefully curated examples and is less versatile or general for entirely novel tasks. So how would you decide when to use which one? So zero-shot chain of thought is best for quick general-purpose reasoning tasks where no examples are available. Few-shot chain of thought excels when examples can be provided. So that is for domain-specific or complex reasoning tasks. So finally, this table shows their capabilities at a glance. So you can take some time looking at it to understand each aspect of the zero-shot and few-shot chain of thought. Both methods have their unique advantages, and zero-shot reasoning offers unmatched flexibility and speed, while few-shot reasoning provides enhanced accuracy for complex tasks. So choosing the right approach again depends on the requirements and constraints of the task that you have at hand. So with that, I'm actually done with the presentation. Thank you.
Questions? Any questions? I have questions for you guys. Today the last day. Okay. Let's see more questions from us. No questions? Well, we have what is common? First of all, what is common? Already. And we have been talking about the reasoning because the CIoT, the cognition, Internet of Things, the main fuel is reasoning, right? We talk about reasoning in many places, and we also saw the reasoning over here. So what is the difference between reasoning we did treated previously and reasoning here? That's one question to think about. Then another thing is we have machine learning and deep learning. Then IoT is using both. So IoT also the planning that IoT can be used this large language model too. Okay, so how this progression of use of this reasoning based techniques is not just reasoning. Reasoning is important for cognition, and that's basically the particular course has focused. And to be the cognition, we have been thinking and talking about the basics of IoT and all those communication infrastructure, pretty much half of that, then we moved here. So, so what we did so far, when keep the last lecture aside, we have started from the infrastructure or IoT, all that process involved, including communication, protocol, everything. Then at the end, we went to the most advanced stuff, yet to be proved for IoTs, but it has a good semantics that you can see from beginning to end is doing reasoning. So there you are using few shots, here few shots. So I want to basically ask you to think a little bit deeper at this point, that what is going on in terms of research for the reasoning and usefulness for the IoTs. Okay. So there is no question for her. Right. Yeah, exactly. So we have actually there are some other students of mine, they are working on say autoencoder and LSTM already, and we didn't have any discussion on those things here, okay, in their program. Did you? I think LSTM we mentioned few places, okay, or maybe there's some things coming up this afternoon too. I mean after this lecture, okay. And we mentioned autoencoder, but we did not use specifically for any applications or any IoTs. Okay, but we know what autoencoder do. So essentially, there are so many things available, and you cannot pinpoint each one and try to get into the course and hold your hand to go through everything. Okay, you try and make a big picture of everything, so that you have your understanding. Not necessarily if a part has been kind of thoroughly proven, but you have been given exposure and given the relationship, connection, communication between those topics. Okay. That's typically, it's like you have, when you suppose I came to the guest house for first time, okay, I don't know anything, it is kind of looking crazy for me, but then somebody showed me, oh, this is the dining area, this is the living room area, this is the bathroom. Once you show these things, then it becomes easier for me to handle it and keep my stay more peaceful, not only peaceful, more productive. Same thing when you attend some workshop like this, you have been given a chance to all the open doors and windows. Then it's up to you how you want to play there or forget that. It's entirely up to you. But no matter what, when you come across some lecture like this or another lecture, is always you have to trigger thinking. You have to think something, not just listening. Listening is only one part. The bigger part is thinking, why this, why not these things. Okay. So I was writing some of the feedbacks for this course. So they are asking me, are there a lot of interaction? Are the students asking questions for that? Did you make an examination of all these things? Okay. So I wish I would have got that questionnaire feedback form beginning of the course, so that I would have engaged that direction. I did not know there is an exam to be there. Okay, I didn't know that. Okay, I knew any time of delivery, the communication class, we expect more interaction questions and providing the thought-provoking questions. Okay, those things. But we did. There are. To say that we had this class, this course, we had a number of good questions. I noticed that. Okay, so it definitely we have more than above average interactions in this program. Okay. Okay. Before I let her go,
please don't mind. I know it's a simple question, but
no, it's okay. Please.
I could try to understand earlier. In few short, we were giving some reference examples.
Right. Few examples.
So in the previous two examples which were discussed,
Mm-hmm.
we are adding some new objects to exist. Like in case of 5, we are adding 3 or 4.
Right.
And then we are saying that this is a model reference for the next example which you are mentioning, like in a 25 are consumed.
Mm-hmm.
Probably it's a different operation.
Right.
Based on the language, it understands that it needs to subtract
So,
from
yeah. So, this is like this. So, you want to answer that? Can you hear that first of all? She can, she can hear that. Okay, I can answer that. Okay. Hmm? Yeah, that's okay. It's fine. Yeah. Now, that's a good question. Even when I read the paper, the same question, same thing thought came to my mind that hey, I am just giving just two things, instances. How it is giving me a broad answer for the next question? That's basically the question. Okay. So you are thinking the pot was empty. You just put two cards, and you get a magic. It's not that actually. You just give those two questions. The whole pot is full of data. The data is directionless. Data was directionless. But when you put two instances, that is a trigger the system that which direction to go. Okay. So when new questions comes, pops up. Okay. Anything else?
that these LLMs require huge computation.
Yes, huge computation.
How will it be feasible in placing this one in edge devices?
Yeah, we know that kind of a scenario is likely to happen, and we attempted. You have seen that after introducing half of the slides on LLM in general, then we are trying to integrate it with LLM. Okay, we have examples all those things. Okay, now we knew that edge cannot do it now. But if you think it cannot do it now, if you stop doing it, then that's the end of the world, right? So, this is what I have in my mind. Okay. LLMs, let LLMs start working. Okay. The three aspects to me that looks beautiful in prospects. First of all, very few questions, very few input you give, you are getting a lot more output. That's more the beautiful thing. Okay. So in the IoT domain, you have lot of examples. You will find that I have few things, but I need to know more about those stuff. So that is promising. At that point, I don't think about the cost. Then, as I said, the pot was full of, because pot was full, computation is more. Okay. Now, if pot is full, where they come from? Due to large amount of computational support. But IoT don't have those support. If you have a lot of data in the pot, then the next question comes, do I need all those data? Because that data has been put there to answer questions randomly coming from everywhere. But if you have a domain specific IoT business, you do not need all those things. Your requirement is much limited. So, you can create a pod to answer everything in that domain if you have data for that domain. Okay. So, we really do not need billions, trillions of data, maybe 500,000 data could be good enough. So, it is a hope that someday we may be able to provide those data with a small computation. And third thing is also coming mind, they call it a large language model. The model is because large. Possibly for domain specific applications, we may get medium level or small level or approximate level, we do not know. This is all new area that we are thinking. So, lot of possibilities there. Okay. So, research is like that. The guy who wrote that paper, attention paper, he never thought that it will be LLM will be huge. So, you start doing research and you never know what direction moving and something pops up beautifully well there. Okay. So, to answer your question, I do not know what you are asking now, but someday me or somebody else will do that. Okay. But we call to go. Sir and go. Source, then how if you put in at A, how the the level for such a large computer process they need. Okay, so yeah, I just told them that one is I believe they put two questions. I mean, two not questions. The third question is not that there are questions going into the system. They had already existing examples. Yeah. By putting those questions, you get answer so that where idea could be explored. So additional questions, more and more, getting more answers, and that's how. And second question is, the world is still waiting, so we don't know the answer. But sometime, maybe medium or small scale specific data might be able to help. Style LLM is a approach, chain of thought. If you have domain specific data and chain of thoughts there, so that is basically that we are going to do. Okay.
Yeah, exactly.
So thank you very much for the nice presentation. You have a lot of patience, not like me. Okay. You read it once more time, 2-3 times, you can connect better. Okay. The research is basically like that. So we can take a good. Oh, what is that connection?